Section 8.2 is on higher order roots. When we talk about higher order, we just mean higher than square roots. So we'll be looking at cube roots, fourth roots or quadric roots, quad roots I want to say. Quadric didn't sound right. Regardless, quintic is fifth roots, sixth roots, higher order roots beyond 2. Most of our focus is going to be on the cube root in this section. So make sure I have mine on. We're going to start by finding the cube roots of perfect cubes. Then we're going to use the calculator to find cube roots and other higher order roots. Finally, we're going to look at how these apply to variables. So for perfect cubes, I recommend that you print out the common squares and cubes paper that's at the top of this new module, or you can just write in your notes some common squares and cubes so that you have the list in front of you. But it's definitely going to become useful as you work through to section 8.3 and beyond. There's going to be times where you really want to have those common squares and cubes handy. When we raise a number to the third power, we're cubing it, we're finding its cube. We can reverse the cubing process to find cube roots of numbers. To find the cube root of 8, we ask what number, when cubed, is equal to 8. It follows that 2 is a cube root of 8 because 2 to the third power equals 8. In other words, 2 times 2 equals 4. The result, 4 times another 2 equals 8. So 2 times 2 times 2 equals 8. The number b is a cube root of a if b cubed equals a. All real numbers have one real number cube root. A positive number has a positive cube root, a negative number has a negative cube root, and the cube root of 0 is 0. So unlike square roots, where technically we add both a positive and negative answer, there's only one possible answer to these cube roots. The cube root of a is denoted by the root symbol with a 3 next to it. So basically this number tells you what number root you're doing. The cube root of a equals b if b to the third power equals a. So same general idea that there's an index number on the root that tells you what root number it is. The entire thing is called a radical. Underneath the root symbol is the radicand. These are some of the most common perfect cubes. I also put 11 and 12 on there for the sheet that I allowed, but if not the sheet, if you don't have the ability to print it out, then I would say at the very least, write these numbers in your notes. You're going to want to have those common cubes handy. Find each cube root. So hopefully if we're looking back at our common cubes, the cube root of 27 is 3. 3 times 3 is 9, times 3 is 27. The cube root of negative 64. Well, if it was just positive 64, it would be 4 times 4 is 16, times 4 is 64. In this case, it's negative 4 times negative 4 equals positive 16, times another negative 4 equals negative 64. As far as signs go when you're dealing with cube roots, if you see a negative underneath, the answer is negative. If you don't see the negative underneath, the answer is positive. But there will be times like this in C where you get a positive answer from the cube root, then multiply it by the negative outside. So to be clear again, the answer to B is negative 4. Here in C, the answer to the cube root of 125 is 5, because 5 times 5 is 25, times 5 is 125. But because of this negative on the outside, the correct answer to problem C would be negative 5. So for the cube root of 27, it equals 3, because we asked what times itself 3 times equals 27, and the answer is 3 times itself 3 times. For the cube root of negative 64, we get negative 4 for the same reason. And then the negative 125 becomes a 5 times that negative becomes negative 5. They show here that you can see it as really a negative 1 that's taken out, times the cube root of 25, or negative 1 times 5 is negative 5. These example problems, all I'm really doing here is saying what times itself 3 times equals this. So we actually just did 27. There's only a few common ones, so apologies that this is a repeat, but basically the cube root of 27 is 3. For 343, again, you have that common list of cubes, hopefully you can find it quickly, but basically 7 times 7 is 49, times 7 again is how I get to 343. For negative 1,000, that's negative 10 times negative 10 gives you 100, times negative 10 gets you to negative 1,000. So the cube root of negative 1,000 is negative 10. We also want to be able to take irrational cube roots, things that I can't just say is something times itself 3 times, and use the calculator in order to find those answers. So you can use the cube root key. So this is showing that if you want to use the x root y key, you press x root y, enter 3, and enter the equal sign. So 7 x root y 3, and then equals means put 7 under the root sign, what root number, the third root, and that'll get you your answer. We're also going to show that you can do it as a fractional power. So normally when I show these examples on the board, I do them as fractional powers because I think that's easier for students to find on their calculators, and it's always written the same way. But again, if you follow these steps, you can use that x root y key if you have it. You also could just do it as the cube root of 7 is really 7 to the power of 1 divided by 3. Essentially, whatever the root number or index is on a root, if you want to take something to an exponent, you write the exponent as the fraction 1 divided by that root number. So since this is a third root, it's the power of 1 divided by 3. To find the value of 7 to the 1/3, we entered 7 to the calculator, 7, then we do y to the x, parentheses, 1 divided by 3, and parentheses. Note that these parentheses are very important because otherwise it'll think that you're taking something to the first power and then dividing that result by 3, instead of the power including the whole thing, 1 divided by 3. So in order of operations, it would see the exponent first and do the 1 first, not the divided by 3 in the exponent first, if you don't include those parentheses. Make sure you're testing that you know how to do it in your calculator by trying to put this in and seeing if you get the same answer that they get. So, if we wanted to take this answer and round it to 1 decimal place, we get 1.9. That would get us back to 6.859, but it's really not that close to 7. If we instead went to 2 decimal places, we're getting closer to 7. If we go to 3 decimal places, we're really close to 7. For most of these answers that you're asked to do in Cengage using your calculator, they say specifically to go to 3 decimal places. So that means we want to look at what the 4th decimal place is. If it's 4 or less, drop it. If it's 5 or more, round up the 3rd decimal place. So cube roots of integers such as 7 and negative 10, which are not integer cubes, are rational numbers. So when we find the cube root of 7 or the cube root of negative 10, we really can't represent them as fractions. Here are 6 problems that we're going to try using the calculator. I'm going to wave to myself as I go try them on the whiteboard. So this is again mostly about trying to figure out how to best do these into your calculator. A lot of calculators do have a cube root button where you can press second something, and if you have square roots, you can also do cube roots. Sometimes there's an x root button where you have to fill in what the x is on the root. Personally, I think the best way to do these is to understand them as fractional powers. Here's what I mean by that. If I put this into my calculator as 2, the thing inside of the radical, to the power of 1 divided by whatever the root number is, that's the same thing as what I've written above. So for square roots, there's usually a square root button that's easy enough, but I could have really written that as to the 1/2 power since it's a second root. I think this is the easiest way that it's going to be to put it into your calculator most likely. This arrow up means to the power of, so it's 2 to the power of 1 divided by 3. That has to be in parentheses, that 1 divided by 3. Otherwise, your calculator is going to read it as 2 to the power of 1, get that answer, and then divide the result by 3. If I put it in the proper way to my calculator and put it in as 2 to the power of parentheses 1 divided by 3, when I do that, my calculator tells me an answer of 1.2599. I'm rounding to the 3rd decimal place. So here, since this is 5 or larger, I'm going to round up. I'm going to make this, really it was a 9, so it becomes a 10. What that means is, instead of this being 59, it becomes 60. For part B, I'm again going to put it into my calculator as 12 to the power of 1 divided by 3. When I do that, 12 to the power of 1 divided by 3 gives me 2.2894. Since the fourth digit is 4 or less, I can just drop that digit. Remember that odd roots, like the third root, can have a negative number inside. Even roots, like square roots we did before, can't have a negative number under them. But there's nothing wrong with the way this is initially phrased. So I need to put in negative 122. So again, negative 122 to the power of 1 divided by 3. When I put that into my calculator, I get negative 4.9596. This is again a case where I'm going to round up. It rounds up to make this 10 really. So what used to be 59 becomes 60. For part D, I'm doing the same thing, but now with negative 322. So again, in the calculator, I'm putting in negative 322 to the power of 1/3. When I do that, I get an answer of negative 6.8541. I'm going to drop that 1 because it's 4 or lower. For these really small numbers, I still do it the same way. I put what's under 0.00057, now taken to the power of 1 divided by 3. When I do that, I get 0.00057 to the power of 1/3 equals 0.0829. Since I'm going to 1, 2, 3 decimal places, I'm rounding to here. That 9 turns that 2 into a 3. So my answer is 0.083. When I do the same, except now for 0.009 negative, I get an answer of negative 0.2080. I can drop the 0 because it's 4 or less. We're now looking to find higher order roots. When I say higher order roots, basically that means something above the cube root, something above the number 3. So an nth root is denoted by n being on the radical symbol with the thing underneath the radical symbol underneath. Basically this n, we're going to see it as a 4, 5, 6, 7, 8, looking at roots beyond just the third root. The number n is called the index of the radical or the root number. If n's an even number, what's going on underneath must be positive or 0. And b must be a positive answer as a result. The reason for that is an even numbered root means that you're multiplying something by itself an even number of times, which can only yield a positive answer. Odd numbered roots don't have that restriction. You can get negative or positive things underneath them. In the square root symbol, where you don't have any index at all, the unwritten index is understood to be 2. So when we did square roots in the past, it had the root symbol but no number. That's because we knew it to be 2 when there is no number. Find each root: the fourth root of 81, the fifth root of 32, the fifth root of negative 32, and the fourth root of negative 81. So for each of them, we're going to determine what number, when raised to the power of the index, produces the radicand. For the fourth root of 81, it equals 3, because 3 times 3 is 9, times 3 is 27, times 3 is 81. I also could have put this into my calculator as parentheses 81 to the power of parentheses 1 divided by 4, and my calculator would have told me 3. The fifth root of 32 is 2, because 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. I can have it as a negative because it's an odd numbered root. I'm allowed to have negative numbers under the root symbol. As opposed to, if I try and do the fourth root of negative 81, 4 is an even number, I can't do an even numbered root of a negative radicand. So there's no real number that is the answer to this. It's undefined or no solution. I'm again going to wave to myself over on the whiteboard. When we're doing these higher ordered roots that are different from the third root, they're really just the same thing, except I'm taking it to a different fractional power. So I still take what's under the root sign, in this case 50, to a power. In this case, 1 divided by 4, because 4 is the number that's on the root. So if I put that into my calculator as 50 to the power of 1 divided by 4, I get an answer of 2.6591. I'm going to drop the 1 because it's 4 or lower. When I do the same thing, except now under a sixth root, I still have 50 on the inside. I still raise it to a fractional power, only this time it's 1 divided by 6 instead of 1 divided by 4. When I do that, I get a final answer of 1.9193. Since this is 4 or lower, I can just drop it. Here I have the same general idea except a negative on the outside, so I need to make sure my final answer is negative, but it's still 50 to the power of 1 divided by the number on the root, in this case 8. So when I do that, I get negative 1.6306. Since this is 5 or larger, I raise 1 more in the decimal place before it. 0 becomes 1. Fifth root of negative 50, because it's an odd numbered root, I can do a negative on the inside. So I can put into my calculator negative 50 to the power of 1 divided by the root number, in this case 5. When I do that, I get a negative answer, which is negative 2.1867. Because this 7 is 5 or larger, when I drop it, I round this number up. It used to be a 6. It becomes a 7. When I go to take the fourth root of 50, the way that I'd write it in my calculator is negative 50 to the power of 1 divided by the root number, which is 4. When I put that in my calculator, it tells me error. The reason it tells me an error is because I have a negative number inside of an even numbered root. I cannot possibly get a negative number from an even numbered root, because if I multiply something by itself an even number of times, even if I started with a negative number, 2 negatives make a positive. If I started with a positive number, 2 positives make a positive. So this is really no solution. There might be a particular way they want you to write it in Cengage. It'll say in the instructions, but basically it's undefined or no solution for that. Here I can take the fourth root of 0.007, so I put it in my calculator, 0.007 to the power of 1 divided by the root number, 4. 0.007 to the power of parentheses 1 divided by 4 and parentheses. I get a final answer of 0.2892, and I'm going to drop that 2 because it's 4 or lower. It's variable expressions. We're going to use the same philosophy that we did when we used square roots. For square roots, we divided whatever the exponent power was by the number 2 because the root number was 2. When we get to these higher order roots, we're going to divide by whatever the root number is. Again, I'm going to do these problems on the whiteboard. Just like we did with square roots, when we go to find these higher order variable roots, we're going to take the current radicand, or the thing under the root sign, and whatever the exponent is on it, we're going to divide it by the root number. So in this first problem, we have x to the 15th. We have a root number of 3, so it becomes x to the 15th over 3, or x to the 5th. For b, we start with x to the 15th now under the 5th root, so it becomes x to the 15th over 5, which reduces to x to the 3rd. This is going to become x to the 28th over 4, which then becomes x to the 7th. this becomes negative x to the 45th over 5, which is negative x to the 9th. Notice, because this is an odd numbered root, I can have a negative underneath that just comes out as a negative. If this root number had instead been 4 or 6, I couldn't do the problem because I cannot have a negative number under an even numbered root. When I get to this problem, I'm going to split it into the cube root of 27 and the cube root of x to the 30th. The cube root of 27 is a perfect cube. I get there by doing 3 times 3 is 9, times 3 is 27. So the 3 comes out. When I deal with x to the 30th under the third root, that becomes x to the 30 divided by 3. So my final answer is 3x to the 10th. For f, this negative stays with the problem. X to the 42nd divided by 3, y to the 6th divided by 3. That really equals negative x to the power of 3 goes into that 10, 14 times, and y to the second power.